Alright, thanks for watching, and today I want to give you an example of implicit differentiation, but in higher dimensions. So consider the following problem. Find partial z over partial x, where z is defined by the following equation: x cubed plus y cubed plus z cubed equals 6xyz. And this is an example of what's called an implicit function. In other words, it turns out here, under certain conditions, which I might talk about at the end, z is actually a function of the other variables, and in this case you can actually find partial z over partial x. So this is an implicit function. And the nice thing is here, we can actually calculate this, and I will show you two methods. One is the direct method, and then the other one, it's kind of a Chen-Lu or implicit method. So the direct method is what I call the Nike method, because you just do it. So just differentiate this with respect to x. So x cubed plus y cubed plus z cubed with respect to x equals 6xyz with respect to x. And now you just have to be careful. You have to figure out what depends on x. Well, x cubed depends on x, of course, but also z depends on x because we want to do partial z over partial x. So y is another variable. We don't really care about it, but you just have to worry that z is actually a function of x. So what you get here is an 3x squared, and then plus Chen-Lu that, so 3z squared times partial z over partial x. And now Prada-Lu that, so we get 6yz plus 6xy partial z over partial x. And notice this is just a system with unknown partial z over partial x. So let's put all the partials on the left-hand side. So partial z over partial x. Now 3z squared minus 6xy, and that becomes 6yz minus 3x squared. And you can just solve for this partial z over partial x, that is 6yz minus 3x squared, and over 3z squared minus 2xy. Wait, what's that? Let me see. Yeah, 6xy. I wrote that. And then, if you want, you can just simplify this a little bit. So 2yz minus x squared, and then, so x squared. And then z squared minus 2xy. So that's one way of doing it. And then there is another way that's kind of useful for more complicated functions, but this is if you want the direct method. Another way of doing it is put everything on the left-hand side. So x cubed plus y cubed plus z cubed minus 6xyz equals 0. And this thing, just call it capital F of xyz. And so in other words, the equation what we have is capital F of xyz equals 0. And how about we take that and differentiate that with respect to x? Because ultimately we want to find zx. And notice, like I said before, there are a bunch of things that depend on x. It's x and z that depend on x. And now all you can do is just use the Chen-Lu. So what we get is the derivative of f in the first slot times dx over dx plus, well, there's no x here, so it doesn't matter, and then plus derivative of f in the last slot times dz over dx. 0x is just 0. And notice this just simplifies to 1. So ultimately what we get is the following thing. You can solve for dz over dx times fz equals minus fx, and then dz over dx equals minus fx over fz. So in other words, another way of obtaining dz over dx, it's simply by, simply by differentiating this with respect to x and with respect to z. So now, just to take the partial derivative of f with respect to x, you get 3x squared plus 0. So again, minus, again, 3x squared plus 0. And again, f here depends on 3 variables. So thinking of z as a variable, z with respect to x now is now 0. So plus 0. And then minus 6yz. And now the same thing, but with respect to z, so 3z squared, if you want 0 plus 0 plus 3z squared, and then minus 6xy. And if you want, which you can just rewrite as minus 3x squared plus 6yz over 3z squared minus 6xy. And you can just divide by 3, and in the end you get the same expression, 2yz minus x squared, and then z squared minus, sorry, that's, wait, yeah, sorry, z squared minus 2xy. Yeah, that's correct. Okay, and that's one thing. And I think the last thing I wanted to say is there's this wonderful thing called the implicit function theorem, which is very useful, and it essentially says this. In other words, suppose you have an equation of this form. F of xyz equals 0. And all that this says is, if the, notice what we want to find here. We want to find dz over dx. So we want to write stuff in terms of x. So the implicit function theorem says, if the derivative of f with respect to what you want to solve for, okay, let me just get this straight. No, sorry, you want to not solve for x, you want to solve for z. Yeah, now remember. Notice, what we had here, we wanted to find dz over dx. So we wanted to solve for z with respect to x. And what the implicit function theorem says is, if the derivative of the function with respect to what you want to solve for, here is z, is not 0, so again, implicit function theorem, if, in this case, again, fz is not 0, let's say at your point or around a certain point, around, let's say, a point AB, some neighborhood of it, then, in fact, around the point AB, z is a function of x and y. So in other words, we can solve for z in terms of x and y, then can solve for z in terms of x and y. Again, not everywhere, but at least around the point. So if you have the point AB, then you can kind of solve for z in terms of x and y. So think z is x squared plus y squared or something. And moreover, we have an explicit formula for the derivative of z, which is given by this one. So you can solve for z in terms of x and y, and moreover, we can calculate the derivative of z with respect to x with the formula that I just erased, which is minus fx over fz. And similarly, for the derivative of z with respect to y, which is minus fy over fc. And again, this is super useful in math theory because you can't always solve for z in terms of something else, but what this tells you is there's an easy way of getting the derivative of z, even though you cannot explicitly solve for it. That's why it's called the implicit function theorem. It's like an implicit function in this case. Alright, I hope you like this little extravaganza. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.